Okay, this is almost perfect. First of all, today I made available the videos and the file that Emanuele Maratti used for introducing R. So they are available from today. And let's see if we can see them later. Okay, now let's go back to rainfall runoff modeling. And basically we stopped here. But our purpose, I just would like to remind you, is to set up a mathematical model describing the rainfall runoff transformation. And I said that this is important for us because it allows us to reconstruct the water resources availability, to reconstruct river flow data. And as I said, the mathematical model should emulate the natural process, the process that we are trying to reproduce, which governs the transformation of rainfall in runoff. And I told you that there are several complex processes that we need to emulate. And we emulate them by setting up a set of mathematical equations. A set of mathematical equations, I say a set because even if, in principle, we have only one unknown, which is the river flow, that we want to simulate, depending on the rainfall, which is only one input. This, in principle, is our problem. Actually, we may have several inputs, and, more important, in order to describe the relationship between input and output, we may need to introduce some state variables in the system. So basically, as you may remember, the system is in principle very simple. We have an input which is rainfall, and an output that is the runoff. And this is the process that we want to emulate with a model. What I said is that in order to describe this relationship, I may need to introduce state variables in the model to quantify the state of the system. And I want to be more clear with a practical example. You can easily understand that the runoff, which is the response of a natural environment to rainfall, depends on the humidity of the natural environment. So you have a portion of land that receives rainfall and gives back runoff. And the response in terms of runoff changes depending on the humidity that is stored by the land that is reacting to rainfall. So this is one issue that for sure we need to take into account. If it rains on a dry soil, the response is different with respect to the situation in which it rains on a wet soil. And therefore, we need to take into account the humidity, for instance. And how can we take humidity into account? By introducing a variable, which is, for instance, average humidity over the portion of land that I'm trying to simulate. And therefore, I am introducing an additional variable. What does this variable do? Basically, this variable, average humidity, quantifies the state of the system which I'm trying to emulate with the mathematical model. So this is one state variable, one example, which means that this variable, again, I'm repeating, quantifies the state of the system. This is why we call them state variables, because with the mathematical model we are trying to emulate a system whose state we may need to describe. And therefore we need to introduce state variables. And of course, if you introduce a variable, a state variable, which is an unknown, then you need additional equation to simulate it. So this is why I say a set of mathematical equations are needed. Depending on the state variables that you introduce to describe the system, you need additional equations. So in principle, the equation that you may need is just one, in principle. But if you want to describe the process with sufficient detail, you may need to introduce state variables and therefore additional equations. So we end up with a set of mathematical equations where the number of equations is equal to the number of unknowns, and then we can solve it. And basically, these equations, not always, but basically, in many cases, they are expressed in differential terms. They are differential equations. Because sometimes it's easier for us to describe in differential terms the system, to describe the changes instead of describing the variables. So it's easier to describe the change in the variables instead of describing the variables themselves. And therefore, in order to describe the variable from the differential equation, we need to compute an integral. So basically, if we express the equations in differential terms, we already know that we need to take an integral to get back to the variables. So for instance, I told you that one of the basic equations that we have is the conservation of mass of water. And I expressed it in this way. dWt over time, dWt over dt, where W is the volume of water which is stored in the considered domain, is equal to, I said, Qt, water in flow in the domain, minus the demand, dt. And therefore you see that this is a differential equation because the volume is described in differential terms. If I want to compute the volume of water that is stored into the system, I need to integrate this equation. But we are very good in mathematics, and so no problem for us to integrate them. And let me say more realistically that now with the numerical integration we can solve problems that we couldn't solve up to maybe 20 years ago. When I graduated in '92. Basically, I used the personal computer for the first time to write down my thesis, my master degree thesis. But we didn't have the computer available for performing computations. So we need to use analytical integration, which is, from a theoretical point of view, more complicated. Let me say that from a theoretical point of view, it's more complicated, but the analytical integration is faster. And from an operational point of view, it's simpler because you don't need to write down a computer program to integrate the equation. So, and also the analytical integration is exact. The numerical integration is affected by uncertainty. And therefore, there are pros and cons if you use numerical integration instead of analytical integration. But anyway, let's move forward and let's recall that in hydrology, which is basically fluid mechanics, we know that the conservation of mass and the conservation of energy are always satisfied, as well as the conservation of momentum. Momentum in Italian is quantità di moto, and basically it's a vectorial form, the conservation of momentum of the conservation of energy. The conservation of momentum we can let's say, loosely define it as a vectorial form of the conservation of energy. And also we know that in fluid mechanics, the Newton laws apply. And let's just call back them in order to briefly remind what Newton laws are, because I'm sure that you know them, but we have also to know them very carefully. So these are three laws. The first one says basically that if you have an object that travels according to uniform motion, the object tends to remain in the same state unless you have an external force that is applied to it. Which means that if you have something moving over the table, this body moving continues to move unless you apply an external force. And of course, your intuition says that the body actually stops moving because there is friction but friction is an external force. In an ideal world where you don't have any resistance to motion, so you don't have any friction, if you just put a body moving on this table, it keeps moving. If it stops, it's because there is friction. So if you roll a ball, the friction is reduced very much, and it continues to move. If you roll my PC, there is a huge friction, so it stops. But the Newton law says that if you don't have an external force, including friction, a body in uniform motion continues to move. And then the second law says basically F equal m times A. So the force is equal to mass times acceleration. So if you want to move a body with a given acceleration, which is A, and you know the mass of the body, the external force that you have to apply to obtain the given acceleration is given by m times A. I'm sure that you know it already. And then for every action there is an equal and opposite reaction. These are the Newton laws. And basically we don't use them in the continuation of this course, but these are the basis of mechanics, and therefore the basis of fluid mechanics and the basis of hydrology. And even if we are engineers, and therefore we need to know how to work in practice, it is extremely important that we have the theory well known and well managed. We need to know where our theory comes from. This is extremely important because it's true that we are engineers, but we are also scientists because we are applying science, and therefore we need to know our roots. Okay, so basically why I'm showing this slide, because I said that I need a set of mathematical equations to describe the model. These are excellent candidates. Okay, and of course you may devise other equations, even empirical ones. You may say, you know, our purpose here is to reproduce Q. In our system, which we want to model with a water balance, we are now trying to reproduce the water availability with the rainfall runoff model, which is Q. And then, if you indicate rainfall with RT, you may say, my model is simply QT, it's equal to alpha times RT. You may say that. You need just one equation because you have one unknown. And therefore, you just may say that there is a linear relationship between Q and R. This is fine. You may do that. The problem would be to estimate alpha. The problem would be to check if the model is reliable. But indeed, you may build such a model. But it's important that you know that even if you do that, which means that you are taking an empirical relationship to describe your process, this empirical relationship has the basis, its basis in physics, and in particular in dynamics. And in particular, you must know that behind this empirical equation, there is implicitly embedded the conservation of mass and energy. So it's extremely important that you know that. You may set up an empirical model because you think that it serves to your purpose, but you must know that beneath this empirical equation there is conservation of mass and energy. Okay? If there is not, it means that your empirical relation cannot work. So if the model that you set up doesn't meet the conservation of mass and energy, it means that something is wrong. So your model cannot be fully reliable. And therefore some people, for instance, build empirical models, but at the end of the story they check if the model keeps the mass balance, because otherwise they conclude that the model is not reliable. Of course, if you tell somebody that it rains 10 and the runoff is 1, it means that something is wrong. Unless you explain that the remaining 9 is evaporated, but you need to describe it. You know, if the mass balance is not correct, there is something wrong. Okay, so let's start from conservation of mass, conservation of energy, and Newton laws. And let's try to make an attempt every time that you use an empirical model to keep in mind that behind the empirical model there is conservation of mass, conservation of energy, and the Newton laws. Okay, good. I think that another important thing that we have to take into account is that usually this rainfall-runoff relationship applies to a portion of land which is quite extended. Usually, if you want to estimate, for instance, the river runoff of the Po River, where does the runoff of the Po River come from? It comes from a huge area, which we call the watershed of the Po River, or the catchment. Catchment, why? Because it catches the rainfall, it catches the rainfall. So we call this area that contributes to the river runoff the watershed, or the catchment. And I don't understand which one of the two, but one is used in the British English and the other one in the American English. Catchment and watershed. They are synonyms, but actually I think that watershed is used in the British English and catchment in the American English. But you have to consider them as synonyms. And some people say river basin, or some people say river catchment, river watershed. So the three terms are catchment, watershed, basin. And let's define what is it. Let's define it better. Okay, so we can define the catchment, watershed, river basin. Somewhere here it's defined, maybe in the next slide. You can define the catchment, watershed, river basin as the, first of all, in reference to a river cross section. So once that you call into play a catchment, implicitly or explicitly, you make reference to a river cross section. It doesn't exist a catchment if you first don't specify the river cross section. And basically you have to tell the name of the river and the location. So for instance, for the Po River, I may say the Po River at Ponte Lagoscuro, which is the last measuring station on the Po River, or I may say the Po River at Piacenza, which is an intermediate station. So I have to specify the name of the river and the location of the cross section. So before defining the catchment, I have to specify the cross section. So for a given cross section, the related catchment or watershed or basin is defined as, I speak slowly and then I repeat, the portion of land which only contributes to the river runoff in the given cross section. I repeat, the portion of land which only contributes to the river runoff or river flow in the given cross section. This is extremely important. I may ask this definition at the exam. So let me repeat it. For a given river cross section, a catchment basin watershed is the portion of land which only, I will explain what only means, which only contributes to the river runoff or river flow or river discharge at the given cross section. So what does it mean only? So let me now draw a river here and let me define, let me assign a river cross section. You remember that the cross section is perpendicular to the average velocity vector in the river. So this is why I draw it perpendicularly to the river course. Let me say. Okay, so I may identify the portion of land such that all the rain that falls here contributes to the river flow in the given cross section. So the question is, does the drop of rain that falls here travel towards the given river cross section? If the reply is yes, it means that this location, which I indicated with a cross, belongs to the catchment. Conversely, if you get another location here, and you see that the drop of rain travels somewhere else, then you conclude that this location is not part of the catchment.
Sorry, the drop of rain must be in the portion of the land, you mean?
Yes. And an important thing is that you should identify all the area that only contributes to this river cross-section. Meaning that if you have a subset of this area, if you have a subset, this is not the catchment, because there are other locations. This is a sub-catchment, but there are other locations that contribute to the runoff in the given river cross-section. So you have to contribute, you have to identify all the area. This is implicit in my definition. The portion of land, okay? And it's important to say that this portion of land, only this portion should contribute to the runoff. Because if you have another portion, like this one, that contributes to the runoff there, then you have to include it in the catchment. So you shouldn't have more contributing there. Okay? So only is important to say, only contributes, which means only that area contributes. There is no more. Because if I drop only, then the definition applies also to the subcatchment. This area, you see, it's contributing to the river flow here. But it's not only this one. There are other locations that contribute. And therefore, it doesn't meet this area, which I highlighted here, doesn't meet the definition that I provided to you before. You have to identify all and only the area that contributes to the river runoff. Okay, so this is our definition of catchment. And you know, it's relatively easy to understand what catchment means. It's not so easy to identify it. If you take a map, it's not easy to identify it, because the usual procedure for identifying the catchment is to follow the dividers, the water dividers. So basically, if you have a mountain here, and you have two sides of the mountain. So basically, if you get a drop falling here, then you assume that this drop travels to this river. And then conversely, if the drop falls here, then it travels to this river. So basically, you follow the divide. In order to identify the catchment, you follow the divide. But the problem is not so easy to solve, because let's suppose that you have in the underground impervious layer like this one, like a rock layer which is impervious. So what happens to the water that infiltrates here? Because once that you get a drop of rain falling over a catchment, and the catchment is permeable, then you get a portion of rain that is infiltrating in the underground, and a portion of rain that flows over the land. But the portion of rain that infiltrates then travels towards the other river. So you see that in this situation, which frequently occurs in practice, because you know that the mountains have usually a rock substrate, because otherwise they wouldn't be there, they would be eroded if they didn't have any rock inside them. Therefore, the mountains are based over rock layers. So you frequently experience actually such a situation. And therefore it's not easy to identify the catchment, because you should say that this side of the mountain, at least part of it, contributes to the river flow in the other catchment, but only for the part that infiltrates. So what you may say is that if it rains very heavily, and the rain doesn't have time to infiltrate, then you get the flow, the rain contributing to the flow in this river. Because you have the majority of the rain that flows as overland flow. But if the rain is not intense, is not intensive, Then the rain has time to infiltrate, and all this side of the mountain contributes to the river flow of the other river. So you see that the processes are a bit complicated. In some cases, you may have this portion of land contributing to one river, in other cases to the other river. So it's not easy to describe these processes. And it's impossible to describe them in detail because you should know too many things which actually we don't know. You should know if there is a rock layer. You should know what is the infiltration potential of this side of the mountain. So you understand why there is uncertainty in hydrology, clearly. But anyway, let's say that if we assume that we are interested in what is called the surface catchment, then you follow the divide and you identify it. Okay? And of course we say that sometimes the subsurface catchment doesn't coincide, is not the same as the surface catchment. Okay, basically, I go back to my reasoning. Your model, which aims to reproduce QT, applies over the whole catchment, so over this whole area. The transformation rainfall to runoff takes place in this whole catchment. So your model applies to a wide area, but actually there is a problem in doing that. The problem is that hydrological processes are highly heterogeneous, which means that they are highly spatially varying. And you can understand that because you can understand that rainfall is spatially varying. We already said that. But more than that, it's spatially varying the properties of the soil. They are spatially varying. So over this catchment, you may have some impervious sections and other sections where you have a high permeability. And therefore, this is the reason for the heterogeneity of hydrological processes. So the problem is that we are trying to apply a model over a wide area to describe a process which is heterogeneous, which means that we cannot apply the model at a so wide scale. Because the model, the mathematical formulation, is the same over the whole catchment. And therefore, basically, we may say that the model is homogeneous. And therefore, we are trying to describe a process that is heterogeneous with an improper mathematical relationship, which means that it's an approximation again. But some people instead solved this problem, proposed to solve this problem by applying the rainfall of model at the local scale. So they decided not to apply, they suggested the idea not to apply the model to the whole catchment, but they suggested to divide the catchment in many small parts and apply a different model to each one of them. And then you have to integrate, of course, the several contributions to the runoff to get the response at the closure of the catchment. The closure of the catchment is called the closure, the river cross-section that you took to identify the catchment. This is called the closure or the outlet. Sometimes it's also called the outlet. So some people suggested to apply not just one unique relationship over the catchment, but, as I said, many relationships on each sub-catchment. And they proposed two different names for these two different modeling approaches. If you apply one unique relationship over the whole catchment, the model is called land. Land. If you decide to adopt several relationships for several subcatchments, the model is called spatially distributed. These spatially distributed models were introduced. The idea was proposed with a famous paper in 1970. But the first operational model that was proposed in the spatially distributed form was proposed to the scientific community in 1986. These are young models. Up to 1970, let me say up to 1990, people, from an operational point of view, used just an AMP model. And the reason why spatially distributed model could become possible is computer availability. Because of course these are more computer intensive, of course, because you substitute one model with several of them. And there were some people that used, as a dimension of these triangles, the length of the sides. Some people proposed to use like 10 meters, which means that the catchment may include like 20,000 formulations that you have to put together. So you understand it's computer intensive. And in this course, let me say, before I say what we are dealing with, when these spatially distributed models were proposed, people started to debate because some operational engineers said that these models require information that is not available in practice. Because of course, if you divide your catchment in 10 parts, you have to describe the soil properties 10 times, not just one. And therefore, some people said we don't have the information for doing that. And so they started to debate, and the debate is still ongoing. Actually, I don't think there is a reply to this debate, because it's important that we have several models available, several modeling approaches, and then, of course, depending on our application, depending on the case study, depending on the purpose of our analysis, we need to be able to select the best one. So if we have enough information, we can use a spatially distributed model. Why not? If we don't have any information on the catchment, then it's meaningless to use a spatially distributed model. And so I think that it's important to have several, as I said, modeling approaches available, and it's important that you know, at least in principle, at least by name, all of them. And then I was saying in this, during this subject, during this course, during my lecture, I will only concentrate on models, because you know, we don't have time to. This is not an hydrology course. This is hydrology and water resources management, and therefore I'm just focusing on an model. Also because we are interested mainly in the theory, and once that you know the theory of LAMP model, you know also the theory of spatially distributed models, because the same equations are applied at local scale instead of the catchment scale. Okay. Now, let me start now with a general premise. I will very rapidly go into the operational part of rainfall runoff modeling, very rapidly, if not today, on Tuesday. But I would like to start, given that this course is called Advanced Hydrology, I would like to start from the very basis of the theory, and therefore I want to mention to you Reynolds transport theorem, because I could skip it. I could just turn to writing the mass balance equation at the catchment scale, because you already know that we need to apply at this stage at the catchment scale, if we use a LAMP model, the mass balance equation, and we need to apply in some way at the catchment scale the conservation of energy. So our domain, so far I talked about a domain. In rainfall runoff modeling, our domain is clearly the catchment, because if the catchment collects all the rainfall that contributes to the runoff in the given river cross-section, it's clear that the mass balance equation should be applied at the catchment scale. So I could just now write it down. But I want instead to give to you just a brief mention on how the mass balance equation is derived, how you can derive it. And if you do some courses on the basic fluid mechanics, and fluid mechanics, which means kinematics and dynamics of fluids, the movement of the fluids, you certainly remember that the continuity equation, which is nothing else than the mass balance equation, was derived by a theorem which is called the transport theorem. Because, you know, a complication is that these fluids whose mass we are trying to balance, these are moving. So these are fluids that are moving. So basically, when you apply your, let's say, the balance equation, you need to identify a body of fluid to which you apply the mass balance equation. So let's suppose that, for instance, for instance, that you have a pipe and some fluid is flowing inside the pipe, and you decide that you want to compute the mass balance equation for this fluid. So one first problem is that you have to identify what is the mass that you want to conserve. And so let's say that we say, okay, I want to conserve this mass of fluid. We cannot say I want to conserve the mass of the pipe, of course. We need to identify the mass of fluid that we want to conserve.